This is Bill Farmer again. Welcome back to Software Engineering 2FA3 Discrete Mathematics and Applications 2. I promised you last time another example of a non-deterministic push-down automata. Here it is. It's M. M has two states, Q0 and Q1. It has two input symbols, A and B. It has two stack symbols, the initial stack symbol and A. And it contains the following transitions. And one thing that you should notice is that if you look at transitions 3 and 4, when we're in state Q0 and on the stack is an A, and we're reading an A, we can do transition 3, or we can do an empty string transition where we don't read the A and we just proceed this way. So 3 and 4 give us options, so this machine is truly non-deterministic. And we're going to see the importance of having two transitions here. Now, this machine accepts by empty stack this set of strings A to the n, B to the n, where n is anything greater than or equal to 0. I'm going to start off with a question. How many configurations are in a computation of M that accepts A to the n, B to the n? So take a moment. Consider what this machine is and see if you can come up with the answer. Okay, welcome back. The answer is C, because basically the way it works, we start with our configuration, our initial configuration, I'll call that C0, and then we're going to have to process the A's. There will be n of them. And then we're going to have to make a transition configuration. I'll just call that D. I'll call that D0. And then we're going to have to process the B's. And there will be n of them. So this is 1 plus n plus 1 plus n. So this is the correct answer. And we're going to see an example in a moment how this works out. Okay, so let's verify that this machine accepts the string A to the 0, B to the 0, which is the same as the empty string by empty stack. Well, here will be the start configuration. We have this transition. If we're not reading anything, we're going to have one of these. We're not reading anything, and we have on top of the stack the initial symbol. We can pop that off and put nothing on it. That puts us into this configuration, which means we will accept the string. We'll accept the empty string. So that's how we accept the empty string. Let's take a simple example. A to the 3, B to the 3, and from this example we will understand how we can accept any string A to the n, B to the n. So this is 3 A's followed by 3 B's. M is going to accept this by empty stack. So if we're reading an A and the initial symbol, which we start off with, according to this transition, we pop this off and we push A. So we get this new configuration. So we've read that. Now we have A on the stack. And so we'll be reading A, and we have this on the stack. We're going to use this transition. We're reading A, we have A in the stack. So the key thing is we take A and we pop it off and we put 2 A's. So we get this new transition. And we're staying in the state Q0, so we do that again, and we get into this configuration. Notice there's no more A's here. Now what we do is we use this transition, which is one of these epsilon transitions We are not going to read anything. We're just going to convert to Q1. We're going to pop off A and put A back. So basically, going from here to here, nothing happens except we change the state to Q1. Now with the state Q1, we can read the B's. Every time we read the B's, we pop off an A. And finally, we read this B, the last B, we pop off an A. We end up in the state that we can accept by empty stack. Okay. The next topic is the equivalence of context-free grammars and non-deterministic push-down automata. So let G be a context-free grammar. Then there will be a non-deterministic push-down automata M that accepts the language of G by empty stack. And that means there will be some other M that accepts it by final state. We know that from a previous theorem. So the proof is given as lecture 24 in Cozen's book. We're going to just briefly sketch the proof below. And the theorem going the other way, if M is a non-deterministic push-down automata, there's going to be a context-free grammar whose language is exactly the accepted language of M by the empty stack method. And the proof of this is in lecture 25 in Cozen's book. Now, if we put these two together, this gives us a wonderful result. Context-free grammars generate and non-deterministic push-down automata accept the same class of languages, the class of context-free languages. So just like regular languages are generated by regular grammars and they're accepted by deterministic finite automata or non-deterministic finite automata, we have a similar situation. Context-free languages are generated by context-free grammars, and then there's a corresponding machine that accepts them, non-deterministic push-down automata. Okay, so this theorem here, we're going to sketch out the proof. We're really not going to show the proof, but we'll look at the key components of it. So let's start with a context-free grammar, G, and we want to produce a non-deterministic push-down automata, M, that accepts the same language as G generates. So what we can do without loss of generality is we can assume all the productions of G have this form, where C is a member of our input alphabet or its epsilon. Now this is almost the Greibach normal form. The Greibach normal form is exactly this, except we would not allow C to be the empty string. But using the Greibach normal form theorem, which says every language that does not include the empty string, there is every context-free language that does not include the empty string has a grammar in Greibach normal form that will accept it. So using that theorem, we can get this result. And so we can assume that all our productions are of this form. And we can construct from G this machine M. You have just one state. You have the same input symbols. It will have as stack symbols, it will have all the non-terminals, and it will have a transition relation. It will have a start state, which is the only state, and it will have a initial stack symbol, which will be S. S will be the start non-terminal, and it will have no final states. We're not interested in final states because we're going to have acceptance by the empty stack. And so delta contains exactly one production. And the production is, if we're in state Q and we're reading C, and C here could be the empty string, or it could be epsilon, and we have A in the stack, what we do is we're going to pop off A and stay in Q and then push this. And we're going to have exactly one of these productions for every, or I should say one of these transitions for every production in P. So when productions in P look like this, for each of these we'll have exactly one transition. And so what we're going to do is M is going to simulate G. It's going to simulate the grammar G. And we can prove a lemma. This is proof by weak induction N. I'm not going to show you the proof here, but you can go and look at what's in Cozen's book. And what this proof says, if from the non-terminal A we can derive Z gamma in n steps via a leftmost derivation, which means we always work on the left. We're always working on the leftmost non-terminal. We can obtain this derivation if and only if there is a computation from, or we can go from this configuration to this configuration. So this configuration says we're looking at the string zy, and we have A on the stack, and then we'll go to just reading y, and then we'll push gamma on the stack. So we're going to assume that this lemma is true. There really is a proof of it. And then this lemma basically will give us the result, because if we start with a string that's generated by a grammar, there's going to be some leftmost derivation that will produce it. And according to this lemma, according to this leftmost derivation, there will be a corresponding run of our machine. And in this case, we're just going to have x. There will be nothing after x. So instead of gamma here, we're going to have epsilon. There's nothing after x, so we have epsilon. And so that means there will be a run that will take us to the configuration that we will accept by empty stack. So that means x will be in the language accepted by empty stack of M. Okay, so let's look at an example. Here's a language L, the language of left and right parentheses that are balanced. We know that there is a context-free grammar for this. Here is a context-free grammar. This is a little different than we've seen before, but because this is actually in Greibach, this special kind of Greibach normal form. The first ones are in Greibach normal form. The second one, instead of having a terminal here, we have basically epsilon string. Okay, so we have this grammar, and we're going to construct a non-deterministic pushdown automata that will simulate it. And here it is. For each of these 5 productions, we're going to have 5 transitions. They all work exactly the same way. Basically, the way it works, we stay in Q in every case. When we're reading this, and this is on the stack, then we will go and we'll end up with putting B in the stack. Same way here. If we're reading this, and this is on the stack, then we put BS. So we can systematically construct this M. Okay, so here is an example. It shows the leftmost derivation of this. So remember, leftmost is we're always working in the leftmost non-terminal. So we apply our production from this, and we get this. Then we apply our production to S, and then we get this. Then we apply our production to B and get this, and so forth. So we get a nice derivation. We can derive this string. we can also accept that string. We start with this string, we apply our rules, and as we're applying the rules, we're pushing these stack symbols on here, which are really non-terminals, and eventually we get to epsilon and we accept. So the machine M very closely simulates the grammar G. Okay, so I want to mention some closure properties. The context-free languages are closed under union, concatenation, and astery, just like the regular languages are. But what's interesting is they're not closed under complementation and intersection. So if we have a context-free language, the complement of that, the language of all the strings that are not in our original language, that may not be context-free. Likewise, if we have two context-free languages and we take the intersection, that may not be context-free. Okay, we're going to stop here, and next time we're going to finish up with this topic on pushed down automata and context-free grammar.